Welcome to the next and I hope last video on this section 13.2 from the textbook Dive into Systems. And so we're going to try to make it to the end of this section in this video. And so here we're talking about exit and wait. So when a process exits, right, and that in C is represented by a system call to the exit call, this basically just causes a cleanup for most of the information. And I don't think it's terribly important for us to understand that in a great amount of detail, just to know that exits the process, frees up the resources. I think that's about all we really need to know about that. But the wait is a little bit different. But I guess before getting to wait, right. And so exits can be triggered in several different ways, sometimes with an explicit call to exit. But if a process performs some kind of invalid action, such as dividing by 0 or dereferencing a null pointer, then that can trigger a further call to an exit. Moreover, if the operating system wanted to reach into a program and force it to exit, basically, then it can do so with what is called a signal. And in fact, that is exactly what happens actually somewhat under the hood when a program, so to speak, tries to divide by 0 or dereference a null pointer. So one signal that has a name here, right? So various signals have their own names, and one signal for a process to terminate a child process running, in some sense spun off from it, is to use this sigkill signal. I honestly don't know if we're actually going to use that information, but there it is. There's a thing called the sigkill signal. And then here, I guess we get some details about exactly what happens to the data after a process has exited. But again, I don't think we're going to need to know those details. Although I could change my mind later, and if I change my mind later, if it turns out that we actually do need to know that for any of the tasks that we're performing, then we can always circle back to it. Now, here we describe the wait system call. And this is what a parent will do when it has some child process and it wants to wait until the child has finished computing whatever it is computing and delivers an answer or something like that. So effectively, this puts the parent on hold, waiting for the child to finish executing. Now, there is also this comment here about how if you didn't want the parent process to be blocked while it is waiting, then you can cause that. And here, this is something that you would enter into the terminal. So if you entered this, the shell process will, because keep in mind, right, the shell is itself a program. And so when you ask for a.out, that shell runs that program. That is effectively the operating system running a new process, that new program that you're running. And you'll perhaps notice that whenever you do that from a terminal, as long as the program a.out is running, then the terminal is blocked. You can't enter anything into the terminal while the program is still running. But what if you didn't want that, right? What if you wanted the shell to free up and basically spin up a completely independent process when it runs this a.out? Well, if you ended it with and, which is often used to join commands together in the terminal, but if you just don't put anything after it, then essentially that just causes the first program to run with no blocking of the shell program. Now, over here, you see how one could structure some code so that there are all of these various forked processes. So what is this going to do? The main program, when this whole thing runs, is going to print A. It's going to fork, and then for the child process only, this block of code is going to execute, meaning that the child will print B, will fork again, and that fork of the fork, right, the child of the child, is going to then run this code, meaning that the sort of grandchild, let's call it, is going to print C, and then spin up this totally new program, a.out. Whereas the sort of first level child is going to do this right here, which is what I suppose it is going to waiting for this grandchild to halt or terminate. And then it will print D, and then it will exit. And the parent of all of this, the grandparent, let's say, then goes on to print E, waits on its child process, and prints F. So effectively what's happening here is you're going to print A, because that happens before any amount of forking. Because these different things may happen in different orders. So is the E gonna print next because the parent goes next? Well, that is CPU dependent, right? So maybe the child gets to go first and prints B, or maybe the parent gets to go first and prints E. That I don't think we can determine. So we know that A goes first. Maybe next is B, although maybe next is E, right? Or at least at the current moment, I think maybe when we go down here to consider what goes down here, we actually might change our minds. Or no, I think I won't change my mind about that. But in any case, so we don't know which comes first, B or E. But then the grandparent process calls wait after that. And so here we guarantee that the next line of code, this printf, will not happen. Will not execute until its child process occurs. So effectively what that guarantees is that the call to print F must come last because it is gonna wait for all the rest of this to execute. Let's see if I am right about that. So in every line here, we are assured that A comes first. In the second line, we see that either B or E could come next. It's not entirely determined. But the very last line is always F, and that is because of that call to wait. And we can tell a somewhat similar story about all the remaining options that could occur here. But basically the idea is that if you don't call wait, then you may not know, which order things will happen in. But a call to wait guarantees that a parent waits for the child to finish executing before it executes. And I guess that's the end. So there we have it. We now have a relatively good understanding of processes, and so in the next video, we will start doing homework assignments or whatever.